Alrighty guys, we're going to go ahead and get started with our momentum notes. So first thing I want to do is talk about the definition of momentum. Like, what is it? And I'm sure you guys have heard momentum before, whether you were playing a sport or something and maybe you made a good play, or maybe your team was losing and your team started coming back and they were like, nice, keep up the momentum. I can't really relate because my team never loses. We just repeatedly win everything. But for some of you guys, maybe you understand what I'm talking about. And in physics, momentum is just the mass in motion. So every object has mass, but not every object is moving. And when those objects do start moving, we can say that they have momentum. So therefore, if an object is moving, it will have momentum. There is an equation for momentum so that we can solve for it if we're given certain information. And that equation is going to be P equals M times V. I know it's kind of funky that we're using the letter P for momentum, but that's just how things work in physics. Sometimes we use weird letters to define weird words. So M is going to stand for mass, we know that. V is going to stand for velocity. And these things are still in their regular units. So mass is going to be kilograms and velocity is going to be meters per second. And P, like we just said, is momentum. And the units of momentum, since it's just mass times velocity, is going to be the units of mass times velocity. So kilograms times meters per second. Let's talk about a few scenarios that involve momentum. The first one I want to talk about is what's happening when we increase one of those values. Well, if I wanted to increase the amount of momentum on an object, what would I have to do? The only way to increase momentum would be to increase mass or velocity. Because if we think about the equation we just talked about, momentum equals mass times velocity. So increasing either of those will increase momentum. On the other hand, if I wanted to decrease the amount of momentum an object has, I would need to do what? Well, I would need to decrease mass or velocity. Because again, momentum equals mass times velocity. They are directly related. As one of those increases, momentum will increase. As one of those decreases, momentum will decrease, assuming you're keeping the other one constant. So is momentum a scalar or a vector? And we talked a little bit about this before, but essentially the difference between scalars and vectors is just that scalars are only numbers and vectors can be positive or negative numbers because the positive or negative tells us a direction. And we're going to say that momentum can be a vector. And the reason why it can be a vector is because momentum can be positive or negative. How do I know it can be positive or negative? Well, momentum depends on velocity. And velocity can be positive or negative. Therefore, momentum will be positive or negative. Again, meaning that it is a vector. Let's talk about the conservation of momentum, if it's conserved or not conserved. So if we're thinking back to things that are conserved, well, we remember that energy is conserved. And momentum is just like energy. So momentum is also conserved. What does this really mean, though? Well, this is going to tell us that momentum cannot be created or destroyed. It can only be transferred from one object to another. And we'll see that once we start doing some labs later on in class, that momentum is really just going from one place to another. Therefore, the amount of momentum at the beginning of the problem must be equal to the amount of momentum at the end of the problem. You cannot create it or destroy it, so what you start with is what you end with. Here I just have a quick little GIF demonstrating the conservation of momentum. I see these light bulbs moving back and forth. So this light bulb hits the next light bulb, and you can see kind of that light traveling through it. Imagine that that light is momentum going from one light bulb on the left side to the other light bulb on the right side. Right here I have a quick little video about this astronaut in space that's really excited to show you how conservation of momentum works with tennis balls.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same.
All right, now that we talked about the basics, let's talk about elastic versus inelastic. So an elastic collision is when two objects collide and then separate after they are in contact with each other. In other words, they are bouncing apart. So we are starting with two objects and ending with two objects. An inelastic collision is when two objects collide and do not separate after contact. In other words, they stick together. So this is a collision where you start with two objects and end with one object. Regardless, though, in either of these collisions, momentum is still conserved. We know that the momentum before, or P before, is equal to the momentum after. But something important to note is that velocity is not always conserved. So it is only conserved if the two objects have equal mass. Here's a quick video about elastic collisions, and I want to show you how when these objects hit each other or collide, that they remain separate. And now on the flip side, here's a video of an inelastic collision where these two objects hit each other and stick together. Alrighty guys, we made it to the end, so let's just go ahead and recap what we talked about. First things first, momentum is just mass in motion. Alright, if you are not moving, you do not have momentum. Momentum is always conserved. So whatever we start with is what we end with. Elastic collisions means that we bounce off. And like we said before, we start with two objects, we end with two objects. Momentum is just mass times velocity. That's our equation. So if we increase mass or velocity, we're going to increase momentum. And if we decrease mass or velocity, we're going to decrease momentum. Right or east is positive, and I have my compass above in case you forgot. And then left or west is negative. Let's quickly recap what we just talked about, some important concepts. And the first one is what happens to the objects after they collide. Well, when objects are colliding, they are going to stick together. And if we said what happens to objects after they explode, we're going to end up with more objects than what we started with. In most cases, we'll just have things explode into two objects, but we could have things explode into 3, 4, 5. The possibilities are endless. What happens to the masses of the objects after they collide? So mass after we collide is just going to add up. We're going to take all those masses from those objects initially, and when they collide and they stick together, we're just going to add all those masses up to figure out the total mass. On the flip side, we would take that initial mass and it would get separated into all these little pieces if we were to explode. Will each object have a separate velocity after they collide? Well, after they collide, they're stuck together, so they will have the same velocity. And again, on the flip side, for an explosion, they will have different velocities. And that's because they're going to have different masses after they explode. But something else I'd like to talk about real quick is what is the velocity initially before an explosion? Well, 99% of the time, that answer is just going to be 0 because our object's going to be at rest before it explodes.